Let's first summarize what we have done so far. Okay. Can everybody see the screen?
Yes, we can.
Okay, great. Now, yesterday we learned about one-dimensional heat conduction. We particularly talked about a slab's geometry, right? We talked about the temperature profile. We obtained the temperature profile in a slab geometry when there is no heat generation, when it's steady state, and when two ends are kept at the same constant temperatures, two different temperatures. Then we learned that the temperature profile is linear, right? Let's say summary. Linear temperature profile. To be able to find this, we talked about Fourier's law, right? We talked about Fourier's law, which was Q, the flux, heat flux along a particular x direction is equal to K, the conductivity. I don't know why this is doing. Okay, K. Yeah, let's erase it. Okay. Minus K dt over dx. I don't know what's going on, but okay. And we learn how to do shell balance. Learned about shell balance. Okay. Yep. There you go. We said if you have a geometry on which you want to study the heat transfer, you can actually take a shell. You can talk about the fluxes coming in, or the amount of heat coming in, amount of heat coming out, and you do basically heat in minus heat out plus heat generation is equal to accumulation, we said, right? And this equation gave us, or this model or this shell balance gave us an equation, that gave the flux Q as a function of position, right? For this particular example, we found it to be like constant. And then we actually used the Fourier's law on top of that, because once you have this Qx, since you know the relation between the Q and the T, then you can actually get the relation between the T and the X. That's how we did. And we found relation between the temperature and the position. So we found basically the temperature profile. And one thing we learned was whenever the temperature gradient is like a decreasing function of position, we said that the flux is going to be towards the x plus x direction. Oh yeah, this was loose. Okay, there you go. But when you have a temperature profile like this, we said that the flux is going to be to the left. Right, so we said that the heat is transferred from larger temperature to lower temperature. As an example, I can actually show you a different profile where you have a fancy temperature profile, not for a steady state without any heat generation, but we're going to see such profiles when there is heat generation. But in such a case, you're going to see that since the temperature profile, the temperature is increasing on the left and decreasing on the right, the heat flux is to the left on the points on the left and to the right on the points here. So heat is actually flowing to the left in this region and flowing to the right in this region. So we are going to see such example. So it's nothing fancy, but you just have a look at how the temperature is changing. If it's increasing, basically, so you have the flux flowing towards the opposite side. Okay, is this clear, everybody? Can you
yes,
hear me?
It's clear.
Okay, good. So that's a summary of one-dimensional steady state heat conduction without any heat generation. Okay. Now, what are we going to do? We're going to solve. Before we solve more problems, I would like to talk a little more about the Fourier's law. More on Fourier's law. Remember, we wrote down the Fourier's law for one dimensions, for flux flowing along the x direction, or dx. What happens if we have flux flowing towards more than one dimensions? Maybe you have like a three-dimensional system, and the flux can be along any direction on your system. So we say for three-dimensional heat transfer, and we're going to be interested in a particular case for isotropic materials. What does isotropic mean? It means the properties of the system does not change depending on which direction you're actually moving. So basically the K is not going to be a function of the direction. In such case, the Q, the vector Q, so it's going to be any direction, so it has x, y, and z components, is equal to minus K, this time not the derivative, but the gradient of the temperature. Okay, and this del is the gradient operator. This is a reminder, by the way. This is you're supposed to know it from your calculus classes. And just as a reminder, in Cartesian coordinates, the gradient of any function f is a vector which has the x component as del f over del x. So the x component is the derivative with respect to x. And if you want to denote the x component, you denote it with like I. So we're going to use the IJK convention here. Plus I means the unit vector along the x direction. Del f over del y, j. J is the unit vector along the y direction. Plus the derivative of function with respect to z, and that gives us the z component, which is denoted by the k, which is unit vector along the z direction. So this is in Cartesian coordinates. In cylindrical coordinates, we have del f equals to del f over. So instead of x, y, z, which coordinates am I gonna have here? Any suggestion? So when we talk about cylindrical coordinates, what are those coordinates?
Radius r.
The radius r, exactly. And who is telling me that?
Sifat Tanvir.
Who?
Sifat Tanvir.
Sifat. Okay, thank you, Sifat. Del f over del r hat plus del f over del theta 1 over r theta hat. There's a suspicious 1 over r term here. Just note that. Plus del f over del z. Yeah. Del f over del z. You can call it z hat. Okay. And in spherical coordinates, the gradient of f is del f over del r hat plus del f over del theta 1 over r theta hat plus del f over del phi 1 over r sine theta phi hat. So here, in Cartesian coordinates, you have the x, y, z coordinates, and the unit vector along the x is the I. This one is j, and this one is k. In cylindrical coordinates, you have cylinder. This is your r direction. This is your z direction. And this is your theta direction. Let's call it. Yeah, let's make this your base. This is your theta. Okay. So you can define any point using r, theta, and z in cylindrical coordinates, and you can define any point in the Cartesian coordinates using x, y, and z, as you know. And in spherical coordinates, this looks like any point here is denoted by r, theta. I'm sorry, it's not the theta. R. This is theta, and this is phi. Okay, that's the spherical coordinates. So this is just a reminder about what gradient operator is and how it can be represented in different coordinates. So if you have a look at this Fourier's law, you can write it for Cartesian coordinates, for example. As Q over bar arrow is equal to minus K times del T over del X I plus del T over del Y J plus del T over del Z K. In the example that we solved in yesterday's class, we did not have this JK terms because this was 0 and this was 0. The reason was we assumed that the heat transfer towards the Y and Z direction or the other directions are negligible. We just assume that temperature does not change along those directions, so there is no flux in those directions. So that's why we only had this term, and we just called it Qx. So this was Qx, this is Qy, this is Qz. Okay. Okay, is that clear so far? Please let me know, yes or no.
Yes, Professor.
Okay, great. Now, before we solve another example, I would like to talk about two more things. I would like to briefly talk about some heat convection. So we are going to learn about the heat convection in details later, but just to be able to solve a couple of problems, I would like to briefly mention what is heat convection and how we can model it in a very crude way. Okay. So we're going to learn what's called as Newton's law of cooling. This is a very basic model to model the convection, and it's also a constitutive equation. It's like the Fourier's law. It's a constitutive equation, and constitutive equation means it's not based on general principles. It's just based on empirical observations or empirical observations or on a very crude model instead of having a fundamental reason behind it. Like, for example, the energy conservation equation is not a constitutive equation. It's a fundamental equation and fundamental law. The Newton's law of cooling or Fourier's law, on the other hand, it's a constitutive equation. It's just a model. It might not be valid for one material, but it might be valid for another material. So it might depend on your system. So when we say constitutive equations, it's just a model, generally empirical. So what Newton's law of cooling says is the following. Imagine you have a material, for example, a slab, and imagine the surface of the slab is at T surface, and that surface is in contact with another a fluid, which is either flowing or just at rest, which is at a temperature Tf. And then imagine that the surface is hotter than the fluid, and you have your Q heat transferred or the flux towards the right-hand side. Okay. And what Newton's law of cooling tells us is the following. Qx, or the flux perpendicular to the surface, which you can also say as the rate of heat flow divided by unit area, is proportional to the differences in the temperatures, Ts minus Tf. So this says that if the temperature difference between the two surfaces is very large, then you're going to get a really large heat flux. If they're very close to each other, almost equal, then you have almost no heat flux between the two surfaces. It makes sense because when you don't have temperature differences, you don't expect the heat to flow from one side to another. It's very similar to Fourier's law, but this time it's not a differential equation. It's not an infinitesimal equation. It's it corresponds to temperature differences at like two separate points far away from each other. Okay, and the proportionality constant constant is be abbreviated as H, is called the heat transfer coefficient. Okay, and you write it as Qx is equal to H times Ts minus Tf, and H depends on the fluid properties as well as fluid velocity. Okay. Later we're going to have we're going to have a better understanding on how H can behave or how H can be calculated for different systems. But let's take it just as granted. This H is given, let's assume. And you can actually find it experimentally if you measure the amount of heat flux and the temperature differences. Then you can calculate the H for a particular system. And the units, as you can see, the units for Qx is watt per meter squared, right? And the units for this is Kelvin, so the H has the units of watts per meter squared Kelvin, right? It's important. So this law is called the Newton's law of cooling. Okay.